In this video, we're going to learn about the applications of triple integrals, mainly volume, average value, and center of mass, and how they extend from the work we've done with double integration. So starting with volume, the volume of the solid bounded by region E can be defined by the triple integral over the region E of 1 dV. So if we're integrating the function equal to 1, this triple integral then represents the volume of the solid defined by E. So an example, find the volume of the tetrahedron bounded by the planes x plus y plus z equals 2, y equals x, y equals 0, and z equals 0. So first, with any triple integral, is to try to sketch the solid as best we can. So x plus y plus z equals 2. So we can go to 2 on each axis. So then we have our intercepts, and we can connect them to create the triangular portion of that plane. So 2, 2, and 2. Then we have y equals x, so we can draw y equals x on the xy plane, and then extend that up parallel to the z-axis. And we have to think about how those two planes intersect with one another. So that's going to be a slanted plane on this vertical plane. So that's going to connect from that point to that point there. And then we have y equals 0 and z equals 0, which are two of the coordinate planes. So if we trace out, because we have a few lines drawn here, if we trace out the solid we're focused on, so we have the xz plane with y equals 0. So we have this piece here, and the axes and the axes. Let's try to draw that a little bit better. All right, then we go on the intersection of y equals x and x plus y plus z equals 2. Then z equals 0 is the xy plane. And then another intersection of the plane x plus y plus z equals 2 and z equals 0. So here is the solid that we're focused on. Just to label everything, so in the front, that's x plus y plus z equals 2. Then on the left side, we have y equals 0. At the bottom, we have z equals 0. And on the right side, that's y equals x. So those are the four planes that define this solid. We can project into any of the three coordinate planes. I think x, y plane is going to be the easiest, so that's our shadow. That's what we're going to use to define the region on the xy plane. So we have y equals x, y equals x. We have y equals 0, so that's our x-axis, y equals 0. And then we need another curve to define a region of integration. So that's where we're going to look right here at the front piece, and that's the intersection of x plus y plus z equals 2 and z equals 0. The intersection of those two planes is right here in front, and the intersection would be x plus y equals 2. So sketching that curve, our region is this triangular region right in here. You can see just how we graphed it, but we can confirm. So let's just write that out. X plus y equals 2. We can confirm algebraically that the intersection would be at the point 1, 1. And now we have all of the piece of information. It's going to be easiest to go left to right, or what we call a type 2 region in the xy plane, to define our bounds. If we went vertically, we would just have to split into two triple integrals. So we want to try to avoid that. So with all of the sketching we've done, we can set up our triple integral. So triple integral of 1. Projection onto the xy plane means z first. So the z equals surfaces that define the solid. At the bottom is z equals 0. And at the top is the plane x plus y plus z equals 2, which is 2 minus x minus y. And then we look at the xy plane and the shadow. So we decided dx dy was the best order of integration. So going from left to right, we're going from y to 2 minus y. Remember, both those need to be x equals. And then along the y-axis, we're covering from 0 to 1. So here's our triple integral that would represent the volume of this solid. Now in this case, we're going to skip over the steps of integrating, and I will tell you that the volume is going to be 2/3. So use this example to practice with your integration techniques, but I think in this particular example, focusing on the bounds and the setup is important. Now, just for connection here, we could have solved this problem with a double integral. We would have taken the double integral over this region on the xy plane, and then our function that we'd be integrating would be the top surface minus the bottom surface. So in this case, 2 minus x minus y minus 0, which is equivalent to now putting those surfaces as the innermost bound of integration. So really, we're just changing the perspective to a problem that we've already been able to solve. So now seeing how it would look from the perspective of a triple integral now. Our next example, find the volume bounded by the surfaces z equals 4 minus y squared, x plus y equals 2, and the coordinate planes. So again, our first task is to make the best sketch that we're able to draw, and then see what the bounds look like. So we have z equals 4 minus y squared, which is going to be a parabolic cylinder. So intercept of 4 on the z-axis, intercept of 2 on the y, a parabolic curve. We don't have to go across the z-axis because the coordinate planes restrict us to the first octant. And then we can extend that out parallel to the x-axis. Right, so there's our parabolic cylinder. Then we have x plus y equals 2, so that's a plane. So 2 on the y, and then 2 on the x. Then we can extend that up vertically. So there's the plane. And then the 3 coordinate planes. So that's the left, the back, and the bottom of this solid. We need to figure out how these two surfaces that we just drew intersect. So we're going to basically see a parabolic curve on this diagonal plane. So we're going to start at this point of intersection and connect it down in a curved, kind of like a parabolic curve, all the way to the bottom point there. So if we take a colored marker just to really highlight this solid. So up top, there's our parabolic cylinder. So that's z equals 4 minus y squared. In the front here, that's the plane. So that's x plus y equals 2. At the bottom, we have z equals 0. On the left, we have y equals 0. And then at the back, so if I draw this along the axes, and then along the back, we have z equals 0. Just to get a sense of where all the planes are and how they're going to be helpful for setting up our bounds of integration. Now, our previous example, we projected onto the xy plane, which is still a viable option here, but let's change it up. Let's project back onto the yz plane. So we're going to cast our shadow in here. Okay, so we're going to go back onto the yz plane. So that region's defined by the parabolic cylinder. So 1, 2, 3, 4, 1, 2. And then we have y equals 0, which is the z-axis, and z equals 0, which is the y-axis. So there's our region. So this is z equals 4 minus y squared, z equals 0, and y equals 0 on each side. Type 1 region makes sense just to go vertically here as far as a region on a two-dimensional plane. So now we can put together the bounds of integration. So triple integral of 1. If we're projecting onto the yz plane, then we're going to go dx first. So x goes from x equals 0. And now that I look here, let's fix that. That back surface should be x equals 0, not z equals 0. That was my mistake. So we're going from 0 all the way out towards us till we hit the plane, which is x plus y equals 2, so 2 minus y. Then based on our projection onto the yz plane, we're going to go dz dy. So z goes from 0 to 4 minus y squared, and then y goes from 0 to 2. Okay, so there's our bounds. We have our order of integration. Now this one we're going to integrate out since we'll use this value in another example. So I have that integral set up for us. So 1 dx dz dy, and you see all the bounds in place. So we'll integrate. So 0 to 2, integral from 0 to 4 minus y squared of x. Evaluate that from 0 to 2 minus y, dz dy. So we're going to go integral from 0 to 2, integral from 0 to 4 minus y squared of 2 minus y, dz dy. Integrating with respect to z now, well, there are no z's, so we get 2z minus yz from 0 to 4 minus y squared dy. So integral from 0 to 2 of 8 minus 2y squared minus 4y plus y cubed dy. So integrating with respect to y, we get 8y minus 2/3 y cubed minus 2y squared plus 1/4 y to the 4th. Evaluate that from 0 to 2. So we get 16 minus 8 times 2/3 is 16 over 3 minus 4 times 2 is 8 plus 16 times 1/4 is 4. So that's going to be 12 minus 16 over 3. So 36 over 3 minus 16 over 3 is 20 over 3. So the volume of that solid is 20 over 3. And we're going to use this value again, so we'll hold on to it. And now we'll build off this into average value. So the average value of a continuous function, f of x, y, z, over a closed bounded region E with positive volume is 1 over the volume of the region E times the triple integral of the function over that same region. So extending the idea of average value now to triple integrals, we're going to divide the triple integral of the function by the volume of the region we're integrating over. So building off that last example, find the average value of the function 2y over the region E bounded by the surfaces z equals 4 minus y squared, x plus y equals 2, and the coordinate planes. So same region, also saves us sketching out in 3 space, which is a huge help. So our volume, just to put that value here, is 20 over 3. Right, and we would hope when we see these examples, it would be a cube or a cylinder, something that we know how to find the volume of without a triple integral. But here, since we already did that computation, it's not more difficult. Okay, so we're going to set up the triple integral. So the same bounds, so we're going to go 0 to 2 minus y, 0 to 4 minus y squared, 0 to 2. Now the function we're integrating is 2y, dx, dz, dy. Integration is going to look very similar to the previous example, so I've gone ahead and done this one out. So it's 112 over 15. And now we can use this value to find the average value of the function. So 1 over the volume, so we can reciprocate, so 3 over 20, times the value of the triple integral, 112 over 15. Now with a little reducing, so 3 and 15 would be 5 and 1. 20 and 112 would be 5 and 28, reducing by a factor of 4 there. So we get 28 over 25 as the average value of this particular function over the defined region. Okay, so volume, triple integral of 1, we can build that into average value, where we're integrating a function over a region and then dividing by the volume of that region, as we saw here. Which leads us to our last application, which is mass, center of mass. So suppose we have a solid object in the shape of a domain E with density function rho of x, y, z. Then the mass of the solid object is defined as the triple integral over the region E of the density function rho dv. So we're extending our idea of mass into 3 space now, where the object whose mass we're able to find is 3-dimensional. So it could be a sphere, a cylinder, a cube. We now have the ability to find the density of a 3-dimensional shape with this triple integral. And if we want to go for the center of mass, we first need to define the moments. So now they're moments about the 3 coordinate planes, since we're in 3 space. So the moment about the YZ plane, well, distance from the YZ plane is x. So we're going to multiply the density function by x. Moment about the XZ plane, distance is y, so we're going to multiply the density function by y and integrate. And then the moment about the XY plane, distance is z, so we're going to multiply z by the density function and integrate. Again, we have a mismatch notation here. Subscript is yz, yet in the triple integral we're multiplying by a factor of x, and it's all based on what we're fixing. If we're fixing the yz plane, then we're measuring the distance from that plane, which is the x coordinate of any point. And we can go through that argument for the other 2 moments as well. Once we find these moments, we can combine them with the mass to find the center of mass. So x bar, y bar, z bar. So the x coordinate is going to be the moment about the yz plane divided by the mass. The y coordinate is the moment about the xz plane divided by the mass. And then the z coordinate is the moment about the xy plane over the mass. Right? And putting all these values together gives us the center of mass. And again, the moments are really just looking at how the density is distributed based off of the distance from one of the coordinate planes. Now, not a crazy extension for mass, but it does result in more integration. So now to find the center of mass, we need 4 triple integrals to be able to compute that. So in a lot of examples, they'll highlight just one coordinate. So they'll say find the x coordinate or the y coordinate or the z coordinate of center of mass to save us a little bit of time and effort. But ultimately, we're doing the same thing each time. So find the center of mass of the solid object that defines the region in the first octant bounded by the planes x plus z equals 1 and y equals 2 with density function rho of x, y, z equaling to 3x, y squared, z. So start by sketching the best possible sketch we can make. So x plus z equals 1. So 1 and 1 on the x and z axes. Connect them. Then we're going to extend that out parallel to the y-axis until we hit y equals 2. And y equals 2 is going to cap this off. Right, so as far as our surfaces here, we have y equals 2. And then in the front, we have x plus z equals 1. In the back, that's x equals 0. On the left side, that's y equals 0. And at the bottom, that's z equals 0. So there are all of the surfaces that define this particular solid, right? And the coordinate planes come from the fact that we're in the first octant. So now let's project onto the xz plane. It's the only plane that we haven't projected onto. Really, any of the coordinate planes work nicely here, but just so that we hit all 3 of our coordinate planes in this video, let's project onto the xz plane. So that's going to be defined by that plane x plus z equals 1. And then the coordinate planes, so x equals 0 on the left and z equals 0 at the bottom. So this region could be defined type 1 or type 2. We'll keep it simple. We'll just go type 1, so vertically through that region. So now setting up the triple integral here. Now we're taking the triple integral of the density function, so 3x y squared z. We're projecting onto the xz plane, so we're integrating with respect to y first. So y goes from y equals 0, and then as we go out, the farthest we get is y equals 2. So those are the 2 surfaces that define the y equals. And then on to the xz plane, we're going from 0 to 1 minus x, if we go dz dx. and then 0 to 1. Right? We're going to need this value to find the center of mass. So one last example where we'll fully integrate, and then we'll skip the integration steps for the remainder. So integrating with respect to y, so we get the integral from 0 to 1, integral from 0 to 1 minus x of x y cubed z, evaluated from 0 to 2, dz dx. So integral from 0 to 1, integral from 0 to 1 minus x of 8xz dz dx. So integral from 0 to 1 of 4xz squared, evaluate that from 0 to 1 minus x dx. So integral from 0 to 1 of 4x times 1 minus x squared dx. Now, this is an example where we have to expand the 1 minus x squared. We wouldn't be able to use a u substitution here because of this factor of x in front. So 1 minus x squared is going to be 1 minus 2x plus x squared. So we can then distribute the 4x across that expression. So integral from 0 to 1 of 4x minus 8x squared plus 4x cubed dx. So we get 2x squared minus 8/3 x cubed plus x to the 4th. Evaluate that from 0 to 1. So 2 minus 8/3 plus 1. So 3 minus 8/3. So that's 9/3 minus 8/3, which is 1/3. So the mass of this region with the given density function is 1/3. Now the moments, to save us a little effort here, I set them all up. I've already done the value, but the moment about the yz plane, we're multiplying the density function by x, and that's going to be 2/15. Moment about the xz plane, so we're multiplying by y, distance from the xz plane, that's going to be 1/2. And then the moment about the xy plane, so multiplying by the distance z, that's going to be 2/15. And the mass, as we just found, was 1/3. So we can combine all these values to find the center of mass. So x bar, y bar, z bar. So that's going to be, that first moment, 2/15 divided by 1/3, which is 2/5. And then we have 1/2 divided by 1/3, so that's 3/2. And then same numbers for the z coordinate, so 2/5. So there is our center of mass. Again, if we were to actually sit and integrate each of these moments out, it would just take a while. It wouldn't be difficult, it would just be lengthy. And then if we wanted to go one step further for the moments of inertia, which we're not going to look at in any examples in this video, but these are the formulas that you would use. So to find the moment of inertia about the x-axis, then you're multiplying the density function by y squared plus z squared, right? Because that would define the radius around the x-axis. And then you can see similar formulas for the moment of inertia about the y or the z-axis. So there are applications. It gives us meaning to triple integrals and why we would study them other than a task of doing another level of integration. And then we're going to see these applications come up again as we extend our triple integrals into both cylindrical and spherical coordinates. So it's important that we understand how to do these problems so when they come up again, we're able to set them up and solve. See you in the next video.